Well, moving on to our final presentation. Likewise, Slido is here on the screen if you'd like to submit a question. If not, you can just ask your questions in person. Now we have Dr. Gabriel Noaje, Principal Solutions Architect at NVIDIA APAC South. Dr. Noaje has more than 15 years of experience in accelerator technologies and parallel computing. Dr. Noaje has a deep understanding of users' requirements in terms of many core architecture after he worked in both enterprise and public sector roles. Prior to joining NVIDIA, he was a senior solutions architect with SGI and HPE, where he was developing solutions for HPC and deep learning customers in APAC. Previously, he was a senior computational scientist at A-Star Computational Resource Center in Singapore, supporting users with deploying their applications on GPUs and large HPC systems. Dr. Noaje holds a PhD in computer sciences from the University of Reims, Champagne-Ardenne, France, and a Bachelor of Science and Master of Science in Computer Sciences from the Polytechnic University of Bucharest, Romania. His topic today, efficient at scale performance using NVIDIA accelerator solutions for HPC and AI. Please join me to welcome Dr. Noaje.
Thank you very much for the introduction. Thank you everyone for being here and for joining this last session. It's our honor to be here. As you've seen in the presentations today, NVIDIA is a partner of NSCC, and the system that is being deployed right now has significantly increased the number of GPUs. So I'm going to talk a little bit about how do we see efficient performance here at NVIDIA. So first of all, NVIDIA is trying to solve big challenges. So we are not looking into solving small problems. There's no point in going after the small issues. So NVIDIA has set a goal to our CEO to go after big challenges, things like climate change, renewable energy, drug discovery, and again, this has been mentioned earlier in the presentations today. COVID has shown us that a lot of computational resources are required and should go into drug discovery, understanding the universe. So all these big challenges require a lot of computational power. The other thing that I wanted to make clear from the beginning, a lot of people still think that NVIDIA is a chip manufacturer, and that's far from being false, because we are doing a lot more than being just producing chips, and even less just as a gaming company. So NVIDIA is a full stack company, and that's what I wanted to show here. Obviously, the hardware still remains the foundation of everything that we're doing. So we have different chips that go into different solution servers, and then they get integrated into systems. But on top of that, we are talking about an entire software stack solution, and it starts with the programming languages. It starts with the libraries, with the high performance libraries that we've been introducing over the years. And then on top of that, we're building the rest of the software ecosystem. Whether we are talking about HPC application, whether we are talking about high performance applications, whether we are talking about deep learning frameworks. And then at the very top, as you can see, we're actually building entire frameworks and solutions that are targeting specifically specific industries or specific verticals, like healthcare, robotics. And how are we going to achieve that goal to solve those grand challenges? Just relying on an incremental performance on the chip itself, it's not enough. And this is an HPC community. You're probably familiar with Moore's law, and this is what you can actually see here with the blue line. And we're actually seeing that in recent years, you're getting to a plateau of Moore's law. So you can no longer expect to just get a new chip and get an increase in performance. So 15 years ago, when NVIDIA first introduced the first programmable GPU, and that's about the time when I started doing GPU computing, the GPUs and accelerated computing was already bringing an order of magnitude increase in performance. And over the years, we managed to, with each new generation, we managed to have a generational leap in performance with each new architecture that we are releasing. But still, that wouldn't be enough. The next step we are looking is scale up and scale out. How to run across multiple GPUs inside of a single server, and how to run across multiple GPUs across an entire system. And again, I'm referencing back to the Aspire 2A system, which has 352 GPUs, and I do hope I will see users that are able to run across hundreds of them and not just one single GPU. And then the next step is bringing machine learning into picture. Traditional HPC has been around for many years, and there are not enough innovations to allow us to have that million x increase in performance in order to be able to tackle those grand challenges. So what NVIDIA is working on is we are considering now the data center as the new unit of compute. So we are no longer just looking at the chip level, at the GPU, at the CPU, at the memory. All the innovation and all the work that we're doing is actually now at the data center level. You probably know that we acquired a couple of years ago Mellanox. Now it's fully integrated into the NVIDIA family. So now we're looking holistically on how to put how to integrate the supercomputer with the rest of the components, how to integrate that with the storage, how to integrate with the edge components, how to integrate with the cloud, and everything obviously interconnected through a fast interconnect network. And as I said, just to give you a couple of examples, and these are new things that we've been working. And I'm going to split my presentation in two parts. First of all, I'm going to focus on the software portion, and then I'm going to focus on the hardware portion. And once again, I want to re-emphasize that I'm starting with the software because software brings a lot of value to the hardware. Just having a new chip or a performant chip or an efficient chip, it's not enough these days. So NVIDIA Modulus, it's a new framework, a new SDK that NVIDIA has launched a couple of months ago. And NVIDIA Modulus is actually bringing deep neural networks into traditional HPC simulations. So NVIDIA Modulus is bringing a new type of neural networks called physics-informed neural networks. And this actually brings deep learning and AI into your traditional simulation. So whether you're talking about solving partial differential equations, which are the foundation of most of the HPC simulations, Modulus will be able to do that through deep learning. Another interesting field that is becoming very hot these days is quantum computing. At NVIDIA, we don't think that, or NVIDIA is not really investing in building a quantum computer or a quantum processor. But we do see the value of quantum computers, and we see a trend of the entire industry going towards quantum computing. And for that reason, we're actually providing now dedicated libraries and dedicated software stack that, together with our chips, allow you to, at this point in the quantum computing evolution, to accelerate the simulation of quantum computers. And there's a lot of work that is being done these days in this field. The other work that NVIDIA is doing, so as you can see, basically I'm actually taking that initial slide with the full software stack and I'm going to the different levels. Modulus is a full complete framework, as well as Quantum, which is a library, and then I'm moving now down into that stack. The other innovation and work that NVIDIA is putting a lot of effort into is performance libraries, and performance libraries are actually at the core of our software technologies. And there are three main pillars for the CUDA performance libraries that NVIDIA is following. Seamless acceleration, make sure that with each new generation, the libraries that we're releasing are taking advantage of all the hardware capabilities. Scaling up and scaling out, and this is something that I mentioned earlier. We want to make sure that the software is able to run seamlessly across multiple GPUs inside of a node and across multiple GPUs across multiple nodes, and composability, basically addressing different device functions. And just again to give you an example, this one of the very used libraries in the HPC space. It's FFT library, Fast Fourier Transform, and this library NVIDIA has been working recently to make a version that seamlessly scales across multiple GPUs. So without going into the details, you can see that the expectation is to get a lot of performance out of the these performance libraries. And last but not least, going even lower down into the software stack is the programming languages. How do you access all the performance that you see in the data sheet for a specific chip? And historically, you might probably know that NVIDIA has been providing the CUDA programming language to access the GPUs. But there's a new effort and a new push to actually standardize and include parallelism into the standard programming languages. So NVIDIA is working with the C++ committees, Fortran committees, and Python committees to make sure that we include parallelism inside those standard programming languages. And we make it easier for the developers to access the performance of these accelerators. CUDA will always be there if you want to squeeze the last bit of performance, but for the vast majority of users, we are pushing into the direction of standard programming languages. All the innovation that we're doing across the software stack also bring another value add to our solution, and that is with each new version of the software stack, or with each new improvement in the software stack, you're actually getting a performance increase on the exact same hardware. So right now, the Aspire 2A is being deployed with A100 GPUs. The performance that you're seeing right now is not the same performance that you've seen 1 year ago or 2 years ago when we started the discussion about deploying the Aspire 2A. And it's not the same performance that you will see in a year from now or 2 years from now. So all the innovation that we're doing in the software stack allows us to actually have a steady increase in performance over the life of a chip. So think back about all the discussion that we're having when you're thinking in terms of performance per watt. So what does performance per watt mean at a certain point in time? If you just look at the raw performance, it might not be a lot. But if you look from an application perspective, the efficiency of a chip is actually increasing over time with the innovation that we're doing at the software level. Similarly, we're working with all the ISV partners. So the innovation that we're doing at the library, the compiler level, they get integrated and upstream together with our partners. So again, over the years, you can see the increase in performance on the exact same chip. Here, for example, I'm showing the A100, again, the same GPU that you have in the Aspire 2A. Now, moving on the hardware side. So, as I said, we're doing a lot of innovation on the software side, and that allows you to get a boost in performance on the exact same architecture. But obviously, we're not standing still. As it was mentioned earlier, we do have our competition who's coming up with new products, and there's a continuous push in between us to come up with new solutions and new innovations. And we are innovating continuously, and we just announced at the beginning of this year the next generation of GPUs, and this is the Hopper architecture, the H100 GPU, which brings just to the innovations in the architecture itself a giant leap in performance. And again, I'm not going to go into all the details and the speeds and feeds of the H100, but this is another step on how we are increasing the or how we are achieving that million x speed up that is required for the grand challenges. And with each new architecture, GPU architecture, we are pushing the boundaries of the efficiency of the chip. Yes, you might think that the overall power consumption for the chip is going up, but you can do a lot more with that chip compared to the previous generation. So efficiency doesn't necessarily mean the inverse of the power consumption. You need to think in terms of performance, and as I said, that performance can grow over time. When we're going one step forward into the direction of system of a chip, we are integrating the interconnect, the networking card, together with ARM cores. We're integrating that with even with GPUs. So you can actually now have an integrated solution called DPUs or Bluefield, where you can actually have the interconnect, you can have the ARM cores, and you can have the GPU chip on the same board. So this will be the next generation H100 converged card, which will have the Ethernet or IB ports. It will have ARM chips, and it will have the new H100 chip. Moving one step forward, so what's coming up next? x86 has been along for quite some time, and it's good for certain jobs, but we think that in order to push the efficient performance even further, you need a new type of CPU. So that's why NVIDIA has been investing for the past couple of years in coming up with our own CPU, and this is the Grace CPU that again was introduced earlier this year. And this will come in two packages. You're going to have a combination of a CPU and a GPU, and this is called the Grace Hopper Super Chip. And then we're going to have the Grace Super Chip, which will actually put together two CPUs on the same packaging. The advantages are many. I'm not going to go again into the details, but just to mention two of them in terms of again the steps that NVIDIA is taking in order to improve the overall efficiency of the chips. First of all, you're going to have the high-speed interconnect between the CPU and the GPU, and that is not possible with the current architecture. We're going to have the NVLink interconnect, which allows you to have up to 900 gigabytes per second. That will drive the interconnectivity between the CPU and the GPU. And secondly, on the CPU itself, you're going to have a specific type of memory called LPDDR5 that normally you find in your smartphones. And rightly so, you might think, how can a memory that is designed for smartphones be good for enterprise and high-performance computing? Well, actually, we worked with our memory provider, and we made a lot of innovations to the traditional LPDDR5 and make it server and enterprise grade ready, bringing things like ECC and a couple of other innovations into the memory packaging. So having a package like this, it will bring a lot of performance. And when I say a lot, you can actually see here if you're looking at the comparison with an x86 server, both for the Grace Hopper Super Chip and the Grace CPU Super Chip. And just to overall all these things, I mean, you can look at it and I can provide you more details, but I want to draw your attention just on the last part here. OpenFOAM, which is a CFD application, and CFD has been brought a lot during the presentations today. Just by having OpenFOAM running on the Grace CPU, you get an increase in performance of 2.2x. So obviously, there's a lot of incentive to move to an ARM architecture. And again, one thing that I want to mention is that the entire ecosystem is already ready for ARM. A lot of people think that it's going to be a huge change to switch to an ARM architecture. The entire ecosystem from the NVIDIA perspective is already ARM ready. So this chip will be available in different flavors. Again, I don't want to go into hardware details too much right now, but all this will provide platforms for different type of workloads, whether we are talking about traditional HPC, professional visualization, or cloud infrastructure. The other innovation that we are doing, as I said, is actually at the data center level, and we're bringing NVLink outside of the box. NVLink has always provided a very fast interconnect at a very low power between the GPUs on the same motherboard. With external NVLink is one of the features and one of the capabilities of the Hopper architecture, and we're bringing the external NVLink outside of the node. So this will allow you to actually connect up to 256 GPUs with the fast interconnect, which is NVLink. And then beyond that, when you want to scale even further at thousands of nodes, you still have the InfiniBand and all the innovations that we are doing at the networking side. Whether we are talking about the Quantum 2 InfiniBand switch, the ConnectX-7 NIC, or all the other additional capabilities that are coming from the Mellanox acquisition. So just to put everything together, again, we're looking at efficiency and how a new system that is built on everything that I mentioned earlier would be more efficient than what we currently have right now. So this is a comparison where we're looking at a 5 petaflops HPC system, and we made a couple of projections. So we're comparing a 2-socket Genoa system with a single Grace super chip. And as you can see, we're getting a 1.8x performance per watt better capability than a standard x86 system, 35% lower OPEX, 50% improved density, and save millions in terms of TCOs. And we can actually work down the numbers if you're interested for your specific use case. This is just an example of how much efficient an ARM system and the ARM ecosystem can actually be. Last but not least, there's been a lot of discussion, and the entire system, the Aspire 2 system, is now moving into being liquid cooled. NVIDIA obviously is not standing still in this field. We are providing and we're bringing capabilities of direct liquid cooling, both for the GPUs and the interconnect. Here, I'm just showing what we announced very recently, that we're going to have a new range of GPUs, starting with the current architecture, the A100, but obviously moving into the next generation that will come with direct liquid cooling capabilities. And just to paint the landscape of where we are, the things that we announced right now is not something that it's in a blurry future. It's actually available right now. We have a number of customers that are already adopted, and we are working to actually deploy systems all across the world, from US, NERSC Perlmutter system, all the way to CSCS in Europe, Chineca, and there are a couple of others that haven't been announced yet, and we'll announce soon. All these systems, again, highly ranked in the Green 500, and as I said, keep in mind that that efficiency is increasing year over year with the innovation that we're doing in the software stack. So, two things to keep in mind. We are now having a steady pace of innovation from the chip perspective. Every 2 years, we expect to have a new generation of chips, whether we're talking about the GPU, the CPU, or the DPU. And last but not least, if there's one single thing to take away from this presentation, keep in mind that efficient computing, it actually requires not just hardware, but it's a conjunction of the entire work that NVIDIA is doing across the hardware stack and the software stack. So with that, this is the end of my presentation. Thank you very much for your time, and I'll be happy to take any questions.
Great, thank you very much. Let's give Dr. Noaje a big round of applause. It looks like the homecoming for you back to Ace now. Welcome back. Okay, so any questions for Dr. Noaje? No one? Everybody's very shy in this room. Maybe just a simple question, because this is tech-like, so from a non-technical-ish perspective. For example, the NSCC's Aspire 2A runs with A100. So, we mentioned that the chips get better and better, more power, efficiency.
Yep.
So how does, can be any data center running A100, for example, one day you come up with maybe something more powerful like the A100X. How does maybe the Aspire 2A or any data center harness the power of a new and more powerful chip, for example?
So, as I said, the power efficiency is coming from two directions. If you're talking about the software perspective, then with each new generation of the software release, basically an HPC center like NSC, they just need to deploy the new libraries, the new compilers that NVIDIA is providing, and out of the box, they'll get that boosted performance on the exact same architecture. They don't have to change anything. Obviously, when you want to move to the next generation, next architecture, we'll probably work to bring that to the data center. It's not necessarily as straightforward in just taking the old one, replacing it with the new one. But the promise, as I said, over the lifetime of the system, and when they're installing the system, it's not going to be for a year or two. It's going to be for at least 3 years, if not 4 or 5 years. The previous system has been around for more than 5 years. And as I said, the promise is over that period of time, on the exact same architecture, you will get an increase in performance. And obviously, that increase in performance means efficiency.
Thank you for the comments. So any other final question to go? Oh, there is on slide, is it? Okay, thank you very much for informing me. Okay, so this question, let's take a look. Just let it load so we can answer the question. I don't see any question here though. Okay, maybe anybody has on slide? Okay, maybe can I borrow your?
Why not just ask?
Yeah, just ask.
Yeah, why not? Just ask the question.
Yeah, hi. So my question is, you know about Windows Direct Storage where they allow games to directly load into GPU? Is there any plans for any development of APIs or something that allows us to load the data directly into GPU for AI model training?
Very good question, and there's actually something that is already done and proven and tested. It's called GPU Direct Storage, and GPU Direct Storage is a solution that combines both hardware and software, and it allows you to load the data directly from an external file system, whether it's NFS or Bluster or GPFS on the HPC side, or as simple as an NVMe drive, and you can load that directly to the GPU. The DMA engine will do all the work for you, and this will work in conjunction with the CUDA programming language. There's a new set of APIs that allows you to control that, and this will go hand in hand with drivers at the kernel level. So we've been working on this. We've had very good results with NASA. We actually had some demos at the ISC and SC in the past 1.5 years right now. So GPU direct storage has been in the work for more than 2 years now. I think about a year ago, it actually became GA, so general availability. And as I said, we do have some interesting benchmarks and some interesting real work application. One of them is with NASA. Another one is with, I'm trying to remember, with CSCS, but I keep forgetting the project. One is with LIGO in the US. So we do have this capability already. So I'll be interested to talk more about this with you.
Thank you for the question. Anybody else? Final call? Okay, great. If not, thank you very much, Dr. Noaje. Can we give Dr.
Thank you
Noaje
very
a
much,
round of applause?
everyone.
Thank